From nebula to humanity, the evolution of life on Earth. The story of our origins is a fascinating journey through time, starting with the birth of the solar system and culminating in the emergence of intelligent life on Earth. From the swirling gas and dust of a nebula to the formation of planets, oceans, and life, the processes that shaped our world are deeply interconnected. Alongside Earth's evolution, humans underwent their own incredible journey, transforming from primitive primates into the highly adaptive species we are today. This exploration combines cosmic, geological, and biological milestones to uncover the remarkable tale of how life and humanity emerged and evolved. Here is a detailed outline of these key events and processes. 1. The formation of the solar system. 1.1. What is a nebula? 1.2. The origin of the solar system. 1.3. Formation of the disk. 1.4. Key elements. 2. Formation of Earth and its early stages. 2.1. Formation of Earth. 2.2. The early atmosphere and oceans. 2.3. The impact of meteorites. 2. Formation of the moon. 2.5. The early geology of Earth. 3. The origin of life on Earth. 3.1. The harsh environment. 3.2. Origin of life. 3.3. Evolution of the early biosphere. 3.4. The early atmosphere. Composition and development. 3.5. Cooling and formation of oceans. 3.6. The role of meteorites and comets in water delivery. Evolution of Earth's atmosphere. 4.1. Evolution of the atmosphere. 4.2. Key processes and events. Summary 5. Human evolution. 5.1. The origins of primates, the early ancestors. 2. The emergence of hominids from apes to humans. 5.3. The rise of the genus Homo. 5.4. The development of larger brains. 5.5. The evolution of Homo sapiens. 6. The role of genetics and culture. 6.1. Genetic evidence and evolution. 6.2. Cultural and technological evolution. 7. Inclusion. 7.1. Ongoing evolution. 8. FAQ section. 8.1. Frequently asked questions about the solar system and human evolution. The nebular hypothesis, the theory of the origin of the solar system. The nebular hypothesis is an important scientific theory that tries to explain how our solar system was formed. It was first proposed in the 18th century by Immanuel Kant and Pierre-Simon Laplace. Let's understand it in detail. 1. What is a nebula? A nebula is a vast cloud of gas, mainly hydrogen and helium, and dust. There are many nebulae in the universe, and stars and planets are born from them. 2. The origin of the solar system. Around 4.6 billion years ago, our solar system was a massive nebula. This nebula began to contract due to the force of gravity. As it contracted, it started spinning, creating intense heat and pressure at the center. This process led to the formation of the sun. 3. Formation of the disk. After the sun was formed, the remaining gas and dust turned into a flat, rotating disk, the protoplanetary disk. At the center, the sun. The majority of the mass of the nebula accumulated at the center, forming the sun. Formation of planets. In the cooler outer layers, solid matter accumulated to form planets. In the inner regions, rocky planets, like Earth and Mars, were formed. In the outer regions, gas giants, like Jupiter and Saturn, formed. 4. Key elements. Gravity. It helped in pulling together the particles of the nebula. Coriolis effect. The spinning disk kept the planets in their orbits. Supernova explosions. Explosions of nearby stars might have also influenced the formation of the nebula by adding heavy elements to the mix. In summary, the nebular hypothesis provides a comprehensive understanding of how our solar system, including the sun, planets, and other celestial bodies, came into existence from a cloud of gas and dust. FAQ section. The nebular hypothesis. What is the nebular hypothesis? The nebular hypothesis is a scientific theory that explains the formation of the solar system. It suggests that the solar system formed from a large cloud of gas and dust, nebula, that contracted under gravity, eventually forming the sun, planets, and other celestial bodies. 2. Proposed the nebular hypothesis. The nebular hypothesis was proposed by Immanuel Kant and Pierre-Simon Laplace in the 18th century. They suggested that the solar system originated from a rotating disk of gas and dust. What is a nebula? A nebula is a large, diffuse cloud of gas and dust in space. It can be the birthplace of stars and planets as the gas and dust particles come together under gravity to form new celestial bodies. 4. How did the sun form according to the nebular hypothesis? According to the hypothesis, as the nebula contracted due to gravity, it began to spin, and the material in the center became increasingly dense and hot, eventually forming the sun. How were the planets formed? The remaining gas and dust surrounding the forming sun flattened into a disk. In the cooler outer regions of the disk, solid particles came together to form rocky planets, while in the warmer inner regions, gas giants formed. What role did gravity play in the formation of the solar system? Gravity played a crucial role in pulling together the particles of gas and dust, causing them to collapse inward. This process allowed for the formation of the sun and planets as the material was drawn toward the center. What is the Coriolis effect, and how does it relate to the nebular hypothesis? The Coriolis effect is a result of the rotation of the disk. It helped shape the orbits of the planets and ensured that they stayed in their respective paths as the nebula continued to spin. How did supernova explosions influence the formation of the solar system? Supernova explosions from nearby stars may have provided the heavy elements that were necessary for the formation of planets, enriching the nebula with these elements before it collapsed. 9. How old is the solar system? According to the nebular hypothesis, the solar system is believed to be around 4.6 billion years old, based on the age of the Sun and other objects in the solar system. What is the significance of the nebular hypothesis? The nebular hypothesis offers a clear explanation for the formation of the solar system, influencing modern understanding of planetary formation and the evolution of stars and their planetary systems. Primitive Earth, the early stages of our planet's formation. The term primitive Earth refers to the earliest stages in the history of our planet, from its formation to the time it began to resemble the Earth we know today. This period is crucial in understanding the conditions that eventually gave rise to life. Let's explore this concept in depth. Formation of Earth. Primitive Earth formed about 4.5 billion years ago from the dust and gas left over after the formation of the Sun. The process is part of the nebular theory of solar system formation, where a rotating disk of gas and dust condenses and gradually forms planets. Accretion. Small particles collided and merged due to gravitational attraction, growing into larger bodies called planetesimals. These planetesimals continued to collide and combine to form protoplanets, eventually leading to the formation of Earth. Differentiation. During this period, Earth was a molten mass. As it cooled, denser materials, such as iron and nickel, sank toward the center, while lighter materials, such as silicates, formed the outer layers. This process created Earth's core, mantle, and crust. The early atmosphere and oceans. Primitive Earth's atmosphere was very different from what we have today. Initially, there was little to no oxygen. Instead, it was composed mainly of gases like methane, CH4, ammonia, carbon dioxide, H2O. Volcanic outgassing. Volcanoes played a major role in releasing gases like carbon dioxide, water vapor, and nitrogen into the early atmosphere. Cooling and condensation. As Earth cooled, the water vapor began to condense, forming the early oceans. The atmosphere was still toxic and lacked free oxygen, creating a harsh environment. The formation of the oceans. The early oceans likely formed from the condensation of water vapor as the planet cooled. These early oceans were rich in dissolved minerals, setting the stage for the chemical processes that eventually led to life. The impact of meteorites. During the Hadean and Archean eons, Earth experienced intense bombardment from meteorites and comets. These impacts were critical in shaping the planet's surface and may have contributed essential elements like water and organic compounds. Panspermia hypothesis. Some scientists suggest that life's building blocks, such as amino acids, could have been delivered to Earth by meteorites or comets. These impacts could have seeded the primitive Earth with the chemical ingredients necessary for life. Formation of the Moon. The Moon is thought to have formed through a giant impact with a Mars-sized body, often referred to as Theia, shortly after Earth's formation. The debris from this impact eventually coalesced to form the Moon. This collision had profound effects on Earth, including the development of tides, a more stable axial tilt, and the lengthening of Earth's day. The first solid crust of Earth was formed as the surface cooled. Initially, the crust was thin and highly unstable, subject to frequent volcanic activity and tectonic movements. Plate tectonics. The movement of Earth's plates began as the crust became more stable, leading to the formation of landmasses and continental drift over millions of years. 6. Origin of life. The origin of life on primitive Earth remains one of the greatest scientific mysteries. Life likely began in the early oceans, possibly near deep-sea hydrothermal vents, where chemical reactions could provide the necessary energy for the formation of organic molecules. Miller-Urey experiment. In 1953, Stanley Miller and Harold Urey conducted an experiment that simulated the conditions of early Earth. They demonstrated that amino acids, the building blocks of life, could be formed from simple inorganic compounds under conditions resembling those of early Earth. RNA world hypothesis. One of the leading theories suggests that life may have begun with self-replicating molecules like RNA, which could store genetic information and catalyze reactions, setting the stage for the development of more complex life forms. 7. The harsh environment. The early Earth was extremely hostile to life as we know it today. There was intense volcanic activity, frequent meteorite impacts, and extreme temperatures. The atmosphere lacked oxygen, and the environment was dominated by toxic gases. However, over time, Earth began to cool, and its surface began to stabilize, paving the way for the emergence of life. 8. Evolution of the early biosphere. Although the first signs of life on Earth are believed to have appeared around 3.8 billion years ago, the evolution of the biosphere was slow. Simple life forms, such as single-celled organisms, began to evolve and eventually gave rise to more complex life forms. Photosynthesis and oxygenation. The evolution of photosynthesis by cyanobacteria around 3 billion years ago led to the production of oxygen, which began to accumulate in the atmosphere. This process, known as the Great Oxygenation Event, eventually made Earth more hospitable to complex life forms. Conclusion. The primitive Earth was a world vastly different from the one we inhabit today. From its violent formation and toxic atmosphere to the gradual cooling that allowed oceans to form, this early period laid the groundwork for life to develop. It was a dynamic and evolving planet, setting the stage for the development of both the Earth's geological features and the diverse life that would follow. Understanding this primordial stage is key to comprehending the Earth's ongoing evolution and the conditions necessary for life. FAQ section. Primitive Earth 1. What is primitive Earth? Primitive Earth refers to the earliest stages of our planet's history, from its formation about 4.5 billion years ago to the time it began developing features like an atmosphere, oceans, and a solid crust, eventually leading to the possibility of life. 2. How was Earth formed? Earth formed through a process called accretion, where small particles of dust and gas from a rotating nebula collided and merged to form planetesimals, which later combined to form the Earth. This process occurred around 4.5 billion years ago. What was the atmosphere of primitive Earth like? The early atmosphere of Earth was primarily composed of gases like methane, ammonia, NH3, carbon dioxide, CO, and water vapor, H2O. There was no free oxygen, and the atmosphere was thick and toxic, which created a hostile environment for life. 4. How did Earth's oceans form? As Earth cooled down after its formation, the water vapor in the atmosphere began to condense, leading to the formation of oceans. These early oceans were rich in dissolved minerals and set the stage for future chemical processes that could give rise to life. What role did meteorites play in primitive Earth? Meteorites and comets played a significant role by bombarding Earth during the Hadean and Archean eons. These impacts could have contributed essential elements like water and organic compounds, possibly aiding in the development of life. 6. What is the panspermia hypothesis? The panspermia hypothesis suggests that life, or the building blocks of life, might have originated from outer space and arrived on Earth through meteorites or comets. This theory speculates that the organic compounds necessary for life may have been delivered to Earth by extraterrestrial objects. 7. How did volcanic activity affect primitive Earth? Volcanic eruptions were a major source of outgassing during the early stages of Earth's history. They released gases such as carbon dioxide, water vapor, and nitrogen, which helped form the early atmosphere and contributed to the planet's heat, further influencing its geological evolution. Why is the study of primitive Earth important? Studying primitive Earth helps us understand how the planet evolved over time, how its atmosphere and oceans formed, and the conditions that may have allowed life to emerge. It also offers insights into the broader processes of planetary formation and the potential for life on other planets. Formation of the atmosphere and oceans, a deep dive into Earth's early stages. The formation of Earth's atmosphere and oceans is a fundamental part of our planet's early history. These two elements were crucial for the development of life as we know it. Here's a detailed exploration of how both the atmosphere and oceans formed. 1. The early atmosphere, composition and development. Volcanic outgassing early in Earth's history during the Hadean eon, around 4.5 to 4 billion years ago. Intense volcanic activity released gases from Earth's interior. This process, known as outgassing, created the planet's first atmosphere. Initially, Earth's atmosphere consisted mainly of water vapor, H2O, carbon dioxide, CO2, methanomonia, NH3. Lack of oxygen. Unlike today, there was no free oxygen, O2, in the early atmosphere. Oxygen was bound in compounds like water, H2O, and carbon dioxide, CO2. This toxic atmosphere created a harsh environment for the development of life as we know it. The greenhouse effect. The high concentration of carbon dioxide and methane trapped heat in Earth's atmosphere, creating a runaway greenhouse effect. This kept the planet's surface incredibly hot, possibly above 100 degrees Celsius, preventing the condensation of water into liquid form. 2. Cooling and formation of oceans. The cooling of Earth. As Earth gradually cooled over millions of years, the temperature dropped enough for the water vapor in the atmosphere to condense and fall as rain. This process was essential for the formation of the early oceans. Formation of the oceans. The first oceans began to form around 4 billion years ago as water accumulated in depressions on Earth's surface. The oceans were initially filled with dissolved minerals and organic compounds. This environment was key for the chemical reactions that would eventually lead to the development of life. Hydrological cycle. As Earth continued to cool, a hydrological cycle began to form. Water from the oceans would evaporate, rise into the atmosphere, and then condense back into liquid form, maintaining the water cycle that we observe today. 3. The role of meteorites and comets in water delivery. Late heavy bombardment. During the Hadean Eon, Earth was bombarded by meteorites and comets, a period known as the Late Heavy Bombardment, about 4.1 to 3.8 billion years ago. These impacts may have played a crucial role in delivering additional water and essential elements to Earth, further contributing to the formation of the oceans. Panspermia hypothesis. Some scientists propose that organic molecules or even microbial life might have been brought to Earth by comets or meteorites, potentially contributing to the origins of life on our planet. 4. Evolution of the atmosphere. Formation of nitrogen and oxygen. Over time, as volcanic activity continued, nitrogen N2 became a major component of Earth's atmosphere. The process of photosynthesis by early life forms, such as cyanobacteria, began to release oxygen, O2, into the atmosphere around 2.4 billion years ago, in what is known as the Great Oxygenation Event. This significantly changed the composition of the atmosphere and set the stage for the rise of more complex life forms. Ozone layer formation. With the increasing concentration of oxygen, the ozone layer, O3, began to form in the upper atmosphere. The ozone layer became crucial for life on Earth as it blocked harmful ultraviolet UV radiation from the sun, allowing life to move from the oceans onto land. 5. Key processes and events. Summary. Outgassing from volcanoes formed the first atmosphere, rich in CO2, CH2, and NH3. Cooling of Earth allowed water vapor to condense, forming the oceans. Meteorite impacts and cometary collisions likely delivered water and organic compounds to the planet. Photosynthesis by early life forms contributed to the buildup of oxygen in the atmosphere. Formation of the ozone layer protected early life from harmful UV radiation. Conclusion. The formation of Earth's atmosphere and oceans was a gradual process shaped by volcanic activity, cooling, and external bombardment. These conditions set the stage for the emergence of life on Earth. The early atmosphere, rich in gases like carbon dioxide and methane, was vastly different from the oxygen-rich atmosphere we have today, and the oceans played a vital role in enabling the complex chemistry necessary for life. FAQ section. Formation of the atmosphere and oceans. Why was the early atmosphere of Earth formed? The early atmosphere of Earth was formed primarily through volcanic outgassing. During the Hadean Eon, volcanic eruptions released gases like water vapor, carbon dioxide, methane, and ammonia into the atmosphere. This created a toxic and inhospitable environment without free oxygen. 2. Why did Earth's early atmosphere lack oxygen? The early atmosphere lacked free oxygen because photosynthesis, which produces oxygen, had not yet evolved. The early atmosphere consisted mostly of gases like carbon dioxide and methane, which did not contain oxygen. 3. When did Earth's oceans begin to form? Earth's oceans began to form around 4 billion years ago when the planet cooled enough for water vapor in the atmosphere to condense. The condensation of water led to rainfall, which accumulated in depressions on the surface, creating the first oceans. 4. What was the composition of the early oceans? The early oceans were rich in dissolved minerals and organic compounds. These minerals were released through volcanic activity, and the presence of these compounds may have been critical in the chemical processes that eventually led to the formation of life. 5. How did Earth's early atmosphere contribute to the planet's temperature? The high concentration of carbon dioxide and methane in Earth's early atmosphere trapped heat through the greenhouse effect. This led to a hotter planet, keeping the surface temperature above 100 degrees Celsius, preventing liquid water from existing until the planet cooled sufficiently. 6. What role did volcanic activity play in forming Earth's early atmosphere? Volcanic activity played a critical role in shaping the early atmosphere by releasing gases like water vapor, carbon dioxide, and nitrogen. This outgassing process contributed to the formation of a thick, toxic atmosphere that was essential for the early development of the planet's surface. 7. How did Earth's cooling affect the formation of oceans? As Earth cooled, the water vapor in the atmosphere began to condense into liquid form, which led to the formation of early oceans. The cooling process allowed rain to accumulate in the surface depressions, eventually leading to large bodies of water. 8. What is the hydrological cycle and how did it begin? The hydrological cycle is the continuous movement of water within the Earth's atmosphere, surface, and subsurface. As Earth cooled and the oceans formed, water would evaporate, rise into the atmosphere, condense, and fall as rain, contributing to the cycle that regulates water distribution on Earth. How did the early oceans support the development of life? The early oceans, rich in minerals and organic compounds, provided the ideal environment for chemical reactions that are thought to have led to the emergence of life. The oceans acted as a primordial soup where life's building blocks could form and evolve. 10. What impact did the early atmosphere and oceans have on Earth's evolution? The early atmosphere and oceans were key factors in Earth's evolutionary history. The greenhouse gases in the atmosphere helped create a stable temperature, while the oceans provided the medium for chemical reactions that set the stage for the origin of life. Over time, as the atmosphere changed and oxygen became abundant, Earth became habitable for complex life forms. How humans evolved, a scientific perspective. Human evolution is a fascinating and complex process that spans millions of years. Through the study of genetics, fossil records, and comparative anatomy, scientists have been able to piece together the story of how modern humans, Homo sapiens, evolved from earlier hominids. Here's a scientific perspective on human evolution. The origins of primates, the early ancestors. The story of human evolution begins long before the appearance of modern humans. Humans are classified as primates, a group that includes lemurs, monkeys, apes, and humans. The first primates appeared around 60 million years ago during the Paleocene epoch. Early primates were small, tree-dwelling creatures that eventually evolved into the more complex forms we see today. Common ancestors. The common ancestor of all primates likely lived in forested environments and adapted to life in the trees, developing traits such as forward-facing eyes for better depth perception. These traits included opposable thumbs for grasping and larger brains relative to body size. The emergence of hominids, from apes to humans. The family of primates called hominids includes all the great apes: gorillas, chimpanzees, orangutans, and humans. The split between the lineages of humans and other apes occurred around 6 to 7 million years ago. Bipedalism, one of the first significant steps in human evolution, was the development of bipedalism, or walking on two legs. This adaptation likely occurred because walking on two legs allowed early hominids to move efficiently across the savannas, see over tall grasses, and free up the hands for tool use. Fossils like Australopithecus afarensis, around 3.9 to 2.9 million years ago, show evidence of bipedalism and are considered some of the earliest ancestors of humans. 3. The rise of the genus Homo. Around 2.5 million years ago, the genus Homo appeared, marking a significant leap in human evolution. Early members of this genus, such as Homo habilis, were the first to show evidence of tool-making, a defining characteristic of human evolution. Homo habilis, known as handy man, this species lived between 2.4 and 1.4 million years ago. They used simple stone tools and are considered the first members of the genus Homo. Homo erectus, which appeared around 1.9 million years ago, is one of the most important ancestors in human evolution. It was the first hominin species to use fire, create more advanced tools, and migrate out of Africa into Asia and Europe. 4. The development of larger brains. One of the most significant trends in human evolution is the increase in brain size. Early hominids had smaller brains compared to modern humans, but over time, the brain volume steadily increased. Brain expansion. The brain of Homo erectus was larger than earlier species, and by the time of Homo sapiens, the brain had evolved to be much larger and more complex than that of any other species. This increase in brain size is believed to be linked to the development of complex social behaviors, problem-solving skills, language, and culture. The evolution of Homo sapiens. The species Homo sapiens, modern humans, emerged around 300,000 years ago in Africa. The evolution of Homo sapiens involved several key factors: tool use and cultural development. Early Homo sapiens began to make more sophisticated tools, engage in art, such as cave paintings, and develop social structures and communication. Migration out of Africa. Around 70,000 to 100,000 years ago, humans began migrating out of Africa, gradually spreading across Europe, Asia, and the Americas. This migration led to the formation of distinct human populations, but all modern humans share a common African origin. 6. Genetic evidence and evolution. Advancements in genetics have provided more insight into human evolution. Studies of mitochondrial DNA and the human genome have shown that genetic relationship with other primates. Humans share about 98% of their DNA with chimpanzees, our closest living relatives, and around 99.9% of our DNA is the same across all human populations. Neanderthals and Denisovans. Genetic evidence also reveals that ancient humans interbred with other hominins, like Neanderthals and Denisovans, which influenced the genetic makeup of modern humans, particularly those of non-African descent. 7. Cultural and technological evolution. Human evolution is not only biological but also cultural. As humans evolved, they developed complex languages, social systems, art, agriculture, and technology. Language. The development of language allowed for better communication, cooperation, and the transmission of knowledge across generations. Agriculture. Around 10,000 years ago, humans transitioned from hunting and gathering to farming, which led to the rise of cities, civilizations, and advanced technologies. 8. Conclusion. Ongoing evolution. Human evolution is an ongoing process. Although modern humans have reached a high level of cultural and technological development, we continue to evolve genetically and adapt to our environment. In summary, human evolution is a complex, gradual process influenced by environmental pressures, genetic changes, and cultural developments. Our ancestors' ability to adapt to changing conditions, develop tools, and communicate paved the way for the rise of modern humans and the diverse world we inhabit today. Frequently asked questions, FAQ, on human evolution. 1. What is human evolution? Human evolution refers to the process by which human beings developed on Earth from now extinct primates. It involves the gradual development of physical and behavioral traits such as bipedalism, walking on two legs, increased brain size, and the use of tools. 2. When did humans first appear on Earth? Modern humans, Homo sapiens, evolved around 300,000 years ago in Africa. However, human evolution spans millions of years, with earlier ancestors like Australopithecus and Homo habilis appearing around 3 to 4 million years ago and 2.5 million years ago, respectively. 3. Who were our earliest human ancestors? Some of the earliest known ancestors of modern humans include species like Australopithecus afarensis, e.g., the famous fossil Lucy, who lived around 3.9 to 2.9 million years ago, and Homo habilis, one of the first to use tools. 4. What are the key stages in human evolution? Key stages include the emergence of bipedalism, the development of larger brains, and the use of tools. Over time, species such as Homo habilis, Homo erectus, and eventually Homo sapiens evolved, each showing advances in technology, social structures, and cognitive abilities. 5. What is the significance of bipedalism in human evolution? Bipedalism, or walking on two legs, was a crucial adaptation that allowed early humans to move efficiently across open landscapes, see over tall grass, and use their hands for tasks like tool-making. Fossils such as Australopithecus show early evidence of this key feature. 6. Did humans evolve directly from chimpanzees? No, humans and chimpanzees share a common ancestor that lived around 6 to 7 million years ago. The two species evolved along separate paths, with humans developing unique traits like walking upright and larger brains. Humans and chimps are more like cousins, not direct ancestors and descendants. 7. What evidence do we have for human evolution? Evidence for human evolution comes from several sources, including fossils, remains of ancient human ancestors, like Homo habilis and Homo erectus, provide insights into their physical characteristics. Genetics, comparative studies of DNA, show how closely related humans are to other primates, especially chimpanzees. Archaeological findings, tools, cave art, and other cultural artifacts show how early humans lived and developed societies. 8. How did the brain evolve in humans? Over millions of years, early hominids developed increasingly larger brains, particularly in the cerebral cortex, which is responsible for higher functions like reasoning, language, and problem-solving. The increase in brain size was closely tied to the development of more complex social behaviors, tool use, and communication. 9. Are humans still evolving today? Yes, humans continue to evolve, although the process is not as dramatic as in earlier stages. Modern human evolution is influenced by factors such as genetics, environmental pressures, and cultural practices. Some examples include resistance to diseases like malaria or the ability to digest lactose in adulthood in certain populations. 10. What role did the environment play in human evolution? The environment played a major role in shaping human evolution. Changes in climate, the spread of forests, and the development of grasslands forced early hominids to adapt to new conditions. The shift to open savannas likely contributed to the development of bipedalism, while climate change may have influenced dietary habits and tool use. The story of human evolution is a testament to resilience, adaptation, and the incredible journey of life. If this fascinating tale inspires you to uncover more about our shared origins, explore scientific breakthroughs, or reconnect with the past, now is the time to dive deeper into this captivating field. The universe has just revealed its secrets. Now it's your turn to share them. Hit the like button if you've uncovered something new today, and let us know your thoughts in the comments. Subscribe and ring the bell to join the cosmic journey, where every video uncovers another piece of the universe's grand puzzle. Share this with a fellow explorer who's ready to unlock the mysteries of life, from nebulae to humanity. The universe is waiting for us. Let's discover it together.